Hello, everyone. My name is Sun Yahui. I am a research fellow in the National University of Singapore. Thank you for coming to my talk today. The topic of my talk is finding group standard trees in graphs with both vertex and edge weights. First, let me introduce the vertex and edge weighted group standard tree problem. Given an undirected vertex and edge weighted graph G and a number of vertex groups, the vertex and edge weighted group standard tree problem is to find a group standard tree in G such that first, this tree contains at least one vertex in each vertex group, and two, the total weight of vertices and edges in this tree is minimized. For example, in this figure, there are three vertex groups. Each vertex group is a set of vertices with the same color. The vertex and edge weighted group standard tree problem is to find a minimum weight tree that contains all three colors. Solving this problem is useful in many scenarios, such as team formation in social networks and region search in cities. Let us formulate this problem mathematically. We consider an undirected graph G, V, E, W, C, where V is a set of vertices, E is a set of edges. W is a function which maps each vertex I to a non-negative vertex weight value Wi, and C is a function which maps each edge E to a non-negative edge weight value Ce. We also consider a set gamma of vertex groups such that each vertex group G belong to gamma is a subset of vertices. That is to say, G is a subset of V. Notably, vertex groups may overlap with each other. The vertex and edge weighted group standard tree problem asks for a tree G dash such that first, this tree contains at least one vertex in each group in gamma, and two, the regulated weight of this tree, namely C lambda G dash equals 1 minus lambda multiply the sum of vertex weights plus lambda multiply the sum of edge weights is minimized, where lambda between 0 and 1 is a regulating weight. This problem is NP hard even when G is a tree and all vertices have 0 weights. We assume that there are at least two vertex groups. The reason is that this problem is trivial when there is only one vertex group. Most existing group standard tree algorithms ignore vertex weights and only consider edge weights. With respect to the existing exact algorithms, the fastest exact algorithm to date, proven DP++ in a 2016 Sigmod paper, relies on techniques that only hold in vertex unweighted scenarios, and thus cannot solve the studied problem. Other exact algorithms that can be used in vertex and edge weighted cases, such as the widely used DPVF algorithm in a 2007 ICDE paper, have exponential time complexities with respect to the number of vertex groups gamma, and are too slow to be implemented in many cases. With respect to the existing non-exact algorithms, to the best of our knowledge, the algorithm in a 2017 SODA paper is the only existing non-exact algorithm that considers vertex weights. It has an approximation guarantee of big O log V log gamma, and a time complexity that is larger than V powered by the square of the tree width of the input graph G, and the tree width often ranges from dozens to hundreds for zero graphs. As a consequence, this algorithm is too slow to be implemented and is of theoretical interest only. Hence, more practical algorithms are required for solving the studied problem. We aim to develop such algorithms in our paper. Initially, we extend a widely used heuristic algorithm from vertex unweighted graphs to vertex and edge weighted graphs. The extension, dubbed XEN Steiner, has a reasonably small time complexity. There are two parts in this algorithm. First, we transform the vertex and edge weighted group standard tree problem to a vertex and edge weighted Steiner tree problem. After this transformation, we solve the vertex and edge-weighted Steiner tree problem. Since the above X-en Steiner has no approximation guarantee for finding group Steiner trees, we further extend a gamma-1 approximation algorithm from vertex unweighted graphs to vertex and edge-weighted graphs. The extension, dubbed X-ELA, has a time complexity proportional to the size of the smallest vertex group, G-mean. Since G-mean can be close to V in practice, X-ELA is too slow to be used when G-mean is large. To address this issue, we propose a new gamma-1 approximation algorithm, dubbed FastApp. The differences between X-ELA and FastApp are as follows. In X-ELA, we find minimum weight passes from vertices to vertex groups, while in FastApp, we find minimum weight passes from vertex groups to vertices. Moreover, in X-ELA, we build G-mean solution trees, while in FastApp, we only build one solution tree. As a result, the time complexities of X-ELA and FastApp are proportional to G-mean and gamma, respectively. In practice, G-mean can be close to V, while gamma is generally below 10 in existing data management applications. Thus, the newly proposed FastApp can be much faster than X-ELA in practice. As a matter of fact, FastApp has the smallest time complexity for approximating group Steiner trees to date. Nevertheless, FastApp does not dominate extended algorithms on practical solution qualities. To attain this dominance while maintaining a high efficiency, we propose another gamma-1 approximation algorithm, dubbed ImproveApp. Its time complexity is close to the time complexity of FastApp in practice. As a result, ImproveApp is also fast in practice. In addition, by employing a dynamical programming-based exact algorithm, we propose a gamma-h+1 approximation algorithm, dubbed partial OPT, where h between 2 and gamma is a tunable parameter. Since the only existing non-exact algorithm in the 2017 Soda paper has an exponential time complexity in general graphs, partial OPT has the tightest polynomial time approximation guarantee to date. To show the competitiveness of our algorithms, we conduct experiments using 3 ZIL datasets and compare 6 state-of-the-art algorithms. We have the list of codes and datasets on GitHub. Some observations are as follows. First, we observe that dynamical programming-based exact algorithms have exponential time complexities with respect to gamma and are too slow to be implemented in many cases. Then, we observe that extended two algorithms, X-en Steiner and X-LA, find better solutions than the vertex unweighted versions in vertex-weighted cases. Furthermore, the extended X-ELA is too slow to be used when G-mean is large, and the proposed partial OPT is also too slow to be implemented in some cases, and thus is mainly of theoretical interest. In the end, we observe that the proposed ImproveApp has a similar speed with the proposed FastApp, and combines superior efficiency and solution quality when it is too slow to find optimal solutions. In summary, the experiments show that while no algorithm is the best in all cases, our algorithms considerably outperform the state-of-the-art in many scenarios. Therefore, it is preferable to use our algorithm to find group Steiner trees in many cases. This is my talk today. Thank you for your time.